Hi all. Today's topic of discussion is about refrigeration and air conditioning. Refrigeration is that branch of science which deals with the transfer of heat from a lower temperature region to higher temperature region in order to maintain a region at lower temperature than its surroundings. So we are all familiar with the basic refrigeration or refrigerator that we have in our house. So basically, the refrigerator, that machine, it actually extracts heat from the space that is inside the refrigerator, which is already at a lower temperature, and rejects that heat to the surroundings, which is at higher temperature, in order to maintain the region inside the refrigerator at a lower temperature. And the system that is used for attaining the process of refrigeration is called refrigeration system. The region which is maintained at a lower temperature than its surroundings is called refrigerated space. So in the case of our household refrigerator, the space that is inside the refrigerator is known as refrigerated space. Now, different methods of refrigeration. So earlier, that is before the development of mechanical systems, natural ice was used as a refrigerant because it absorbs, when ice melts, it absorbs the latent heat required for its melting from the surroundings. Thus, it cools the surroundings. Now we have different mechanical refrigeration systems which include vapor compression refrigeration system, vapor absorption refrigeration system, air refrigeration system, and steam refrigeration system. In air refrigeration system, high pressure air is allowed to expand to lower pressure. When air expands, its temperature reduces. The low temperature air is used for refrigerating the region. So that is the working of air refrigeration system. Next, steam refrigeration system. In steam refrigeration system, the steam is allowed to expand from a higher pressure to very low pressure using a nozzle. Now this creates a very low pressure region near the nozzle exit. At very low pressure, water evaporates at a very low temperature. When water evaporates at low temperature, it absorbs heat from the space for evaporation, thus refrigerating the region. So that is the working of steam refrigeration. Then comes vapor compression refrigeration system and vapor absorption refrigeration system. In both vapor compression and vapor absorption, the refrigeration is carried out by using a working fluid of low boiling point, and this working fluid is called as refrigerant. when the when the refrigerant is allowed to evaporate the surrounding region to be refrigerated, the refrigerant absorbs the latent heat required for vaporization from the region and thus cooling the region. So basically these two systems, that is vapor compression and vapor absorption system, utilizes a very low boiling point liquid known as refrigerant, and this refrigerant, when it vaporizes, it absorbs the heat from the surroundings. That is the latent heat of vaporization of the refrigerant, and due to which the surroundings gets cooled. So these are different mechanical refrigeration systems. Next is applications of refrigeration. Major applications of refrigeration are long preservation and transportation of food items without spoiling, preserving life-saving drugs, vaccines, etc., used as medical and surgical aid in operation theaters, ICUs, etc., providing working environment for efficient operation of computers, precision machines, then used for liquefaction of gases for several engineering applications. These are some of the applications of refrigeration. Moving on, next term is ton or ton of refrigeration or tonnage. So ton is actually the capacity of refrigeration. So capacity of refrigerating machine is generally expressed in terms of ton or tonnage. 1 ton of refrigeration is defined as the amount of refrigerating effect produced by uniform melting of 1 ton of ice from and at 0 degrees Celsius in 24 hours. So when 1 ton of ice melts, 1 ton of ice which is at 0 degrees Celsius melts uniformly in 24 hours, for its melting it actually absorbs heat from the surroundings, right? So the amount of heat that is absorbed from the surroundings or the refrigerating effect produced is known as 1 ton of refrigeration. Next is a term known as coefficient of performance, COP. Coefficient of performance, COP. So the performance of a refrigerating machine is expressed by a factor called coefficient of performance. Coefficient of performance or COP is defined as a ratio of desired effect to work input. It is a ratio of desired effect to work input. Okay. Now we'll compare between a heat engine, a refrigerator, and heat pump. So here, Figure A shows a heat engine, figure B shows a refrigerator, and C shows a heat pump. And we can see that we have a higher temperature body, which is known as source, and a low temperature cold body known as sink. And here we have a heat engine which is working between these two source and sink. So here this heat engine, it actually absorbs heat from a higher temperature source, Q2 amount of heat, rejects Q1 amount of heat to a lower temperature sink, and the difference Q2 minus Q1 is converted to a work output W suffix E. So that is a working of heat engine. Now a refrigerator, it actually absorbs or it receives or it takes heat from a lower temperature body, that is a sink. So this cold body is a sink. It takes Q1 amount of heat from this cold body or sink, and it rejects Q2 amount of heat to the hot body or the source. Now for this process, the refrigerator consumes an amount of work W suffix R. So the refrigerator takes in an amount of work W suffix R. Next is heat pump. Now heat pump, the aim of heat pump is to supply heat to a higher temperature source. So here we have a heat pump working between a lower temperature body known as sink and a higher temperature body known as source. Now this heat pump actually pumps heat from this cold body or sink and gives an amount of heat Q2 to this higher temperature body or source. For this process, the pump consumes an amount of work W suffix P. So the aim of heat pump is actually to supply heat to this hot temperature body, and the aim of refrigerator is to absorb heat from the cold temperature body. The aim of a heat engine is to give a work output W suffix C. Okay. Now we'll differentiate these. So this is actually the differentiation between a heat engine, refrigerator, and a heat pump. And now again, see, for the case of a heat engine, the efficiency of heat engine, efficiency is actually output by input. So the heat engine actually, it is used to give a work output W suffix C. So efficiency of heat engine is equal to W suffix C, that is a work output given by the energy consumed for that work output. It consumes an amount of heat Q2 for giving this work output W suffix C. So the efficiency of a heat engine is equal to W suffix C by Q2. Now for the case of a refrigerator and heat pump, we will be using the term known as COP, coefficient of performance, for rating the performance. So for the refrigerator COP is actually the ratio of desired effective work input. The desired effect of a refrigerator is to absorb Q1 amount of heat from the cold temperature body. So Q1, for that it consumes an amount of work WR. So Q1 by WR is the COP of a refrigerator. For the case of a heat pump, the desired effect is to supply Q2 amount of heat to this higher temperature body. For that it consumes an amount of work W suffix P. So COP of a heat pump is equal to Q2, desired effect is Q2 by it consumes WP amount of work. So this is the differentiation between heat engine, heat pump and refrigerator. Now refrigerants. A refrigerant is the working fluid that is employed in a mechanical refrigeration system. It carries heat from a lower temperature region and rejects heat to a higher temperature region. So the refrigerant should have some desirable properties. Okay, so now we know what a refrigerant is. Next we will be seeing the desirable properties of refrigerants. First one is latent heat of refrigerant must be high so that the desired refrigeration can be achieved with less amount of refrigerant. Now that is actually self-explanatory, because if the latent heat is more, then it will be able to absorb more amount of heat and you need to use only less amount of refrigerant. Specific volume of refrigerant vapor must be low so that the size of compressor can be made small. The saturation pressure of the refrigerant at desired temperature must be slightly above atmospheric pressure so as to avoid the leakage of refrigerant from the evaporator. The refrigerant must be non-flammable and non-explosive. The freezing point of the refrigerant should be lower than its evaporating temperature. The leakage detection of refrigerant should be easy. Cost of the refrigerant should be low and should be easily available, and the refrigerant must be non-corrosive. Now these are some of the desirable properties of the refrigerant. There are more properties, but these are some of the important desirable properties of the refrigerants. Now talking about refrigerants, We might have heard of CFC free refrigerants, that is CFC refrigerants or chlorofluorocarbon refrigerants. Chlorofluorocarbon refrigerants, usually of the halocarbon family, they usually belong to halocarbon family of refrigerants, which include examples of such refrigerants are R11, R12, R114, etc. They contain chlorine atom. So CFC, chlorofluorocarbon, CFC in the presence of sunlight, chlorofluorocarbons in the presence of sunlight may split releasing chlorine atoms. These chlorine atoms will react with the ozone in the atmosphere and they release free oxygen radicals, thus splitting the ozone layer. Now we know that the ozone layer or ozone gas is actually it provides a protective layer over our Earth's atmosphere, preventing the entry of UV light and radiations, harmful radiations from the sun. So the release of this CFC refrigerants or chlorine from the CFC refrigerant will erode the ozone layer, okay, or it will lead to the depletion of the ozone layer. So this creates serious impact because UV rays reaching the Earth's surface can cause an increase in skin cancer, increase in eye disease, reduction in immunity against disease, harmful effects to crops, wildlife, marine life, etc. So the relative ability of any substance to deplete ozone layer is called ozone depletion potential or ODP. This is important. The relative ability of any substance to deplete ozone layer is called ozone depletion potential or ODP. Similarly, CFC refrigerants have high ODP and high global warming potential or GWP. So, what is global warming potential? It is the ability of a substance to contribute towards global warming. So, in this scenario, we have eco-friendly refrigerants. Eco-friendly refrigerants are those refrigerants that are friendly to the ecology with lower ozone depletion potential and global warming potential. Example are R134A, ammonia, etc. So actually, United Nations through their environmental program has persuaded many nations under Montreal Protocol to stop manufacturing of CFC refrigerants, and now usually the refrigerants used are eco-friendly refrigerants. Now we'll be seeing a reversed Carnot cycle. Actually, Carnot cycle, we have seen Carnot cycle earlier in our class, and Carnot cycle, it forms the basic working cycle which gives you the highest efficiency that is possible. Similarly, for the working of refrigeration or refrigeration system, we have a reverse Carnot cycle. Now we know that in Carnot cycle all processes are actually reversible. So by reversing the process in the Carnot cycle, we get reversed Carnot cycle. Unless Carnot heat engine, Carnot refrigeration cycle undergoes a reverse process. That is, it acts in a reverse way as that of the Carnot heat engine. It absorbs heat from a lower temperature sink. That is what is meant. Undergoes a reverse process. That means that it absorbs heat from a lower temperature sink and rejects it to a higher temperature source by consuming an amount of work. Whereas heat engine actually received heat from a higher temperature source, rejected heat to a lower temperature sink, and produced an amount of work. So in that way, Carnot cycle, reversed Carnot cycle works in a reverse manner as compared to Carnot heat engine. The reverse Carnot cycle consists of two reversible processes, that is two reversible isothermal and two reversible adiabatic process. So this is basically the layout. See here, this is our Carnot refrigerator. It absorbs heat from lower temperature sink by consuming an amount of work W and rejects heat to a high temperature source. The reverse Carnot cycle is drawn on PV, pressure volume, and temperature entropy diagram, TS diagram. Here we have actually two processes. One is a reversible isothermal process and another one is a reversible adiabatic process. Okay, so the processes are actually shown on PV, a pressure volume, and temperature entropy diagram. So here when you take the temperature entropy diagram, the process 1 to 2 is a reversible adiabatic process, 2 to 3 is an isothermal process. Here 1 to 2 is reversible adiabatic, 2 to 3 is isothermal process, reversible isothermal process, 3 to 4 is reversible adiabatic process, and 4 to 1 is reversible isothermal process. So 1 to 2 is a reversible adiabatic. Reversible adiabatic is also known as isentropic. So it is a vertical straight line here, isentropic process, entropy same. Then 2 to 3 is a reversible isothermal process, so temperature should remain same. So it is a horizontal line on temperature entropy diagram. 3 to 4 is a reversible adiabatic process, which is also known as isentropic. So it is a vertical line on the TS diagram. 4 to 1 is again isothermal process, which is a horizontal line on TS diagram, because here temperature is constant. Now we have to find out the COP, or coefficient of performance. Coefficient of performance is the ratio of desired effect to work input. The desired effect here is absorption of heat, that is Q suffix L, from lower temperature reservoir, and for that W amount of heat is W reversible, W amount of heat is consumed. So QL by W is COP, which is equal to QL by QH minus QL, because this work consumed is the difference between heat rejected and heat absorbed, QH minus QL. So this is equal to, now Q is actually TDS, the heat that is supplied can be written as T into DS, that is temperature into change in entropy. So QL, heat that is absorbed, so heat absorption process is happening in process 4 to 1. 4 to 1 is the heat absorption process in process 4 to 1, which is a reversible isothermal process where heat is absorbed, and heat is rejected during the process 2 to 3. So heat absorption and heat rejection happens isothermally. 2 to 3, which is isothermal heat rejection process, and 4 to 1 is isothermal heat absorption process. So heat that is absorbed QL is equal to temperature TL into temperature TL. TL is the temperature, it is a lower temperature, that is T4 equal to T1, that is TL. TL into change in entropy is S1 minus S4. Okay. So TL into S1 minus S4 is the amount of heat absorbed, because Q is actually T into DS, temperature into change in entropy DS. Similarly, QH, that is the heat rejected. Heat rejection happens in process 2 to 3 isothermally. So here the temperature is T2 equal to T3, which is equal to TH, that is higher temperature. So TH into S2 minus S3, TH into S2 minus S3, minus again QL is actually TL, which is equal to T4 equal to T1, TL into S1 minus S4. So here S1 entropy at point 1 is actually equal to entropy at point 2, and S4 is equal to S3. Therefore here S1 minus S4, S2 minus S3, and S1 minus S4, this is actually common term which can be cancelled out, because both the here S2 is actually equal to S1, this can be written as S1, and S3 can be written as S4, so this becomes equal to S1 minus S4. So this is a common term which cancels out, and we'll get TL by TH minus TL, that is temperature at the sink, or lowest temperature, by highest temperature minus lowest temperature. So this is the expression for COP of a reversed Carnot cycle. Now the coefficient of performance of a reverse Carnot cycle depends only on the highest temperature and the lowest temperature. It depends only on lowest temperature and highest temperature. Normally TH is greater than TL, that is the highest temperature is greater than lowest temperature. So mean COP of a refrigerant, will be usually greater than 1. COP of a heat pump is also greater than 1. Now COP of a heat pump is equal to COP of refrigerator plus 1. Okay, and if we decrease the lower temperature, both COP of refrigerator and COP of heat pump decreases. Next is vapor compression refrigeration system, VCRS, vapor compression refrigeration system, or VCRS. So this is the most practical form of mechanical refrigeration system employed for commercial and domestic applications. The basic components of VCRS are compressor, condenser, expansion valve, and evaporator. So we can see here you have a compressor. This is the compressor. So 1 to 2 is the compression process. Then we have a condenser. 2 to 3 is the condensation process. Then expansion valve. 3 to 4 is the expansion process. And then evaporator. 4 to 1 is the evaporation process. Okay. So the function of a compressor is to take in the lower temperature refrigerant vapor from the evaporator. So from the evaporator, a low temperature, low pressure vapor is coming, vapor refrigerant. So the compressor will take in the vapor refrigerant and compress it to a very high temperature and high pressure. So at this point 2, we have high pressure, high temperature vapor refrigerant. Okay, and this vapor refrigerant at state point 2 actually moves to a condenser. So inside the condenser, This high pressure, high temperature vapor refrigerant condenses by rejecting an amount of heat QH to the surroundings. So after condensation, the refrigerant becomes liquid. At point 3, it is liquid refrigerant, but at high pressure and high temperature, it expands in the expansion valve. So process 3 to 4 is expansion process. Now the expansion is actually isenthalpic, that is enthalpy here remains same. During expansion process, the liquid refrigerant expands. So after expansion, the refrigerant pressure decreases, temperature decreases, due to which some refrigerant may become a vapor. Okay, let us assume that everything is in liquid state. So we have low pressure, low temperature liquid refrigerant. This refrigerant moves to evaporator. So process 4 to 1 is evaporation process, where the liquid refrigerant absorbs the heat from the heat that is present inside the evaporator, and it gets converted to vapor refrigerant, which is again at low pressure. So at state point 1 you will have low pressure, low temperature vapor refrigerant. So basically it is the evaporator from where the heat is absorbed, okay, and the heat is rejected in the condenser. So this is the basic working of a vapor compression refrigeration system. Now, this vapor compression refrigeration system is actually represented on pressure enthalpy chart and temperature entropy chart. Pressure, enthalpy, and temperature entropy chart. So, we will see the different process that is happening here. So, basically, we will start from state point 1 to state point 2. At state point 1, we will be having saturated vapor refrigerant. So, here at state point 1 it is vapor refrigerant, because see this line you are seeing here, this is actually saturated liquid line. Saturated liquid line. So, everything that is to the left, that is this region, is liquid. That is, it is marked as subcooled liquid region. So, here the refrigerant will be in liquid state, whereas inside, okay, now this line is saturated vapor line. This curve you are seeing here, this is saturated vapor line. They both meet at this point. This point is known as critical point. So everything that is to the right of saturated vapor line is superheated vapor. So this region contains superheated vapor, and anything that is in between or inside this curve, that is between the saturated liquid region and vapor region, this is wet vapor. Okay, so at this point it is saturated vapor. So saturated refrigerant or vapor refrigerant is compressed by the compressor. Now this compression process is reversible adiabatic compression or isentropic compression. Okay, so the compression process reversible adiabatic or isentropic compression from state point 1 to 2. So at point 2 you have a high pressure, high temperature, that is superheated vapor. Now process 2 to 3 is condensation. During condensation process, the refrigerant rejects its heat to the surroundings and it condenses. So from 2 to 3 condensation process happens, which is constant pressure process. So you have a constant pressure condensation process, okay, where the heat is rejected to the surroundings. Then process 3 to 4. So at point 3 we have saturated liquid. So here we can see that refrigerant has reached the saturated liquid line, or this is the saturated liquid line. Now 3 to 4 is expansion process, which is isenthalpic expansion. 3 to 4 is isenthalpic expansion process, where the refrigerant expands. So after expansion the pressure has reduced and it has become a wet vapor. So it can be either vapor or liquid, that depends on where you stop this condensation process. Now you need not stop it here, you can actually extend it backwards, that is also possible, but here it has stopped here, due to which after expansion we have got wet vapor region, which is a mixture of vapor and liquid refrigerant. And 4 to 1 is the evaporation process, where heat is absorbed by the refrigerant. So here again evaporation process is a constant pressure process, where the saturated liquid plus vapor refrigerant actually, or wet refrigerant actually absorbs the heat and it gets converted to a dry saturated vapor refrigerant. Okay, so the basic process are 1 to 2. 1 to 2 is reversible adiabatic or isentropic compression. 2 to 3 is constant pressure condensation. 3 to 4 is isenthalpic expansion, and 4 to 1 is constant pressure evaporation process. The same process has been shown on temperature entropy diagram. Here 1 to 2 is a vertical straight line because it is reversible adiabatic or isentropic compression. 2 to 3 is a constant pressure heat rejection process. So here the refrigerant is actually condensing, so the temperature reduces, temperature of the superheated vapor actually reduces until it reaches saturated vapor. Now from saturated vapor onwards, here phase change is happening. So during phase change, that is the saturated vapor is getting converted to saturated liquid. So vapor converting to liquid is a phase change that is happening. During phase change, temperature remains constant. Though it is a constant pressure process, 2 to 3, though it is constant pressure, during this region, since it is phase change, here temperature also remains constant, due to which the temperature is also constant here, and it reaches saturated liquid region, saturated liquid at point 3. 3 to 4 is isenthalpic expansion process, and 4 to 1 is constant pressure heat addition process. Though it is constant pressure heat addition, here again phase change is happening. During phase change, temperature also remains constant, so it is shown as a constant temperature process here. Okay. Now, COP of vapor compression refrigeration system, COP is equal to the desired refrigerating effect by work supply. That is, desired refrigerating effect is to absorb heat from the evaporator. So heat is absorbed from the refrigeration region, and for which work is supplied for the refrigerator. So heat that is absorbed in the evaporator or the refrigerator region is actually the enthalpy difference between 1 and 4, that is H1 minus H4, by work that is supplied for refrigeration. Work is supplied by the compressor, so the enthalpy difference is H2 minus H1. So H1 minus H4 by H2 minus H1 is the COP, coefficient of performance of a vapor compression refrigeration system. Okay, so that is about refrigeration system. Now moving on, next we need to study about air conditioning also. So while studying about air conditioning, we need to know a term known as psychrometry. Okay, so psychrometry is that branch of science that deals with study of moist air. Study of moist air. So what is moist air? Moist air is a mixture of dry air and water vapor. It is a mixture of dry air and water vapor. Now, air conditioning is the process of controlling and maintaining the internal atmosphere in a confined space. So, actually, air conditioning involves controlling the simultaneous control of temperature, humidity, motion of air, and purity of air in the region of interest. So, if you want to have air conditioning system in a room, you need to simultaneously control the temperature, humidity, motion of air, and purity of air, whereas refrigeration involves only controlling the temperature of that region. Okay, so air conditioning is a bit more complicated phenomenon, and here you need to know about the humidity or the amount of moisture that is present in air. For that we need to study the study about psychrometry. So it is the branch of science that deals with study of moist air. Now, psychrometric properties. There are some psychrometric properties that we need to know. It is simple. One is dry bulb temperature, known as DBT. It is the temperature of atmospheric air measured by ordinary thermometer. Next is wet bulb temperature, WBT. It is the temperature of atmospheric air measured by thermometer whose bulb is covered by a wet cloth or wick. Next is dew point temperature. It is the temperature of atmospheric air at which water vapor present in the air starts to condense. Then specific humidity, it is defined as the ratio of mass of water vapor to mass of dry air present in a given volume of atmospheric air. Then relative humidity, it is the ratio of actual mass of water vapor to mass of water vapor present in the same volume of air when it is saturated at the same temperature and pressure. So this chart is actually known as psychrometric chart. The psychrometric process can be represented in psychrometric chart. Okay, so we'll be dealing with psychrometric chart and psychrometric process. So here a psychrometric chart is actually shown. The chart, x-axis of the chart is actually dry bulb temperature. This is the origin. The x-axis is dry bulb temperature or DBT temperature. Y-axis is specific humidity omega. Then we have a curve over here. Okay, so this curve actually shows wet bulb temperature. Okay, wet bulb temperature can be marked here. It is marked here. Wet bulb temperature is marked here, and this curve is actually the saturation line or the saturation curve, which has 100% relative humidity, 100% relative humidity line. And curves can be drawn parallel to 100% saturation line, relative humidity line, which represents different relative humidity. So this line might represent a relative humidity of say 65%. Similarly, a line can be drawn here which represents will be here which represents a relative humidity of say 75%, etc. Okay, so uh, now here I have already told that wet bulb temperature is marked here. Now wet bulb temperature can be obtained by drawing an inclined line like this. This inclined line actually shows the wet bulb temperature. It is marked here only. Similarly, specific volume is also marked, which is a differently inclined line. A differently inclined line here will show a specific volume, which is also marked here. So basically, the importance of psychrometric chart is that this chart contains different psychrometric parameters. So if you know at least two parameters, like if you know the dry bulb temperature and relative humidity, you can plot a point with relative humidity and dry bulb temperature. You can plot a point here, this point O. So at this point O, you can find out the specific humidity by drawing a horizontal line like this. This will give specific humidity here. It will be marked here. Now from here you draw, you move through this wet bulb temperature line, and here you will get the wet bulb temperature. Okay, you move through the specific volume line, you will get the specific volume here. So if you know at least two properties, the rest of the properties can be easily obtained from psychrometric chart. Now we have different psychrometric process. Okay, first process is sensible heating. Sensible heating represents an increase in dry bulb temperature, without change in specific humidity. See, specific humidity is not changing, therefore it is a horizontal line. It is marked as horizontal line. This is actually a psychrometric chart, and sensible heating is marked here. It is a horizontal line where dry bulb temperature is increasing, but specific humidity remains constant. Next is sensible cooling, where dry bulb temperature decreases, but specific humidity remains constant. Specific humidity is marked on the y-axis actually. It remains constant. Next is humidification and dehumidification. So this is humidification process where specific humidity increases but dry bulb temperature remains constant. Therefore, it's a vertical line upwards. Next is dehumidification, where humidity decreases but dry bulb temperature remains constant. Therefore, it is also a vertical line downwards. So next is combination of these processes. One is heating and humidification. So heating actually temperature increases. Okay, temperature increases, so but humidity remains constant. So you have done heating, and then you need to humidify. For humidification, you will go vertically upwards, like right, humidification. So this is the final point here. So it can be actually represented as a line like this. This represents heating and humidification, because this is heating and this is humidification. So combination heating and humidification is represented by an inclined line. Then next process is maybe heating and dehumidification. So this is heating, this is dehumidification. So this represents heating and dehumidification. Next is cooling and humidification. This is cooling, this is humidification. So a line like this represents cooling and humidification. Next is cooling and dehumidification. This is cooling, this is dehumidification. So this line represents cooling and dehumidification. So these are the different psychrometric processes. Okay. Next is different types of air conditioning system. Basically, we have central and unitary air conditioning systems. Okay, unitary air conditioning system include window air conditioning and split air conditioning. So unitary means it is used, it is for a particular room or a particular confined space. Air conditioning is done. That is unitary air conditioning. Unitary air conditioning include window air conditioning. So window air conditioning was used earlier, where it is actually a box type device which will be fixed onto the wall. So the wall will be cut, the entire wall will be cut as a rectangular block, and then you will fix the entire refrigerating unit into the wall. One half will be outside the wall, that is facing the atmosphere, another half will be inside the room. Okay, so that is window air conditioning. Here I have explained split air conditioning system. Split is the modern air conditioning system that is used. That is why I have given the figure of split air conditioning. So this is also similar to window air conditioning, except that you need not cut an entire hole, but only a small hole is required for connections. For the case of window air conditioning, you will have to cut this wall here and here, so that a rectangular space is formed, and you will fix the entire box here. But instead of that, in modern split air conditioning systems, we have a split system where the separate indoor and outdoor units are here. This is the indoor unit which is inside the room. This is the wall, and this is the outdoor unit that is outside the room. So the indoor, let us first see the indoor system. So here actually the air from the atmosphere is coming in through here. Okay, the air is coming in, and it comes to the evaporator. This is the evaporator. Okay, so the evaporator has a refrigerant which absorbs the heat from this air, and the air becomes colder and moves out. This is the casing. So here it is the casing. The cold air moves out. Hot air from the room comes in through here. The evaporator, which contains refrigerant, absorbs the heat from the air, and the air becomes cold and it moves out. So the refrigerant, which has absorbed the heat from the air, becomes vapor state. That vapor state refrigerant moves through this point, comes here, it comes to the compressor where it is compressed to high temperature, high pressure. Then it moves to the condenser where it rejects its heat to the atmosphere, and then it comes here. Okay, through this line it comes and comes to the throttling valve, which is the expansion device where it expands and becomes liquid form. That comes to the evaporator, again it absorbs heat. So this is the line that is happening. The outdoor unit actually consists of, this is the outdoor unit which consists of, this is the casing, consists of a compressor and condenser which goes in the outside. Okay, so the air from atmosphere comes in, it takes in the heat from the condenser and moves out. So basically compressor is the unit that produces sound, so it is placed outside so that the sound of the compressor is not heard inside the room, and the condenser is also outside. So the outdoor unit consists of a compressor and condenser, indoor unit consists of evaporator and expansion device. This is the layout of unitary air conditioning or split air conditioning system. Similarly, you can have window air conditioning also. If this was a window air conditioning system, then this would have been a single box like this, entire box like this. Okay, which also has outdoor and indoor unit, but it will be a single box. Here it is two different boxes which are only connections are given through the wall. Next is central air conditioning system. Now the central air conditioning system is usually used in hospitals, malls, etc. So here actually the difference is that here the entire processing will be happening at a place, and then the conditioned air will be supplied to the rooms by using duct arrangements. Okay, so here the outdoor or fresh air is coming in. So we have a mixing box here, and let be there. Now the fresh air comes in. The air is actually preheated once, and then it is given to a cooling coil where it is cooled. After cooling, it is reheated again to adjust for the temperature, and then a humidification, if any required, is done and is given to the supply air fan. From the supply air fan, we have long ducts moving, so the conditioned air will move through the duct and it will reach the required space. Now the return air is actually coming through here. Return air, some amount is exhausted, and some amount of air is passed through a filter to the mixing box where it mixes with the fresh air, and then again it undergoes the same conditioning process. So if the air coming in is actually cold, then can be preheated, okay, to the required temperature. In that case, cooling will be off, and preheated air will be given to the reheat coil where it, if needed, can be reheated and humidified if required. Similarly, if it is a hot air that is coming in, the preheating will not be done, it will be cooled. Now if the cooling exceeds the required limit, then a slight reheating can be done, and if humidification is required, can be humidified and supplied. So basically in central air conditioning system, the processing will be happening at a single space, and the air will be carried to the required space using a large number of ducts. Okay. So this is the type of air conditioning system, central and unitary air conditioning system. So thank you, and wishing you all a happy learning.